If you've been into FPV for any length of time, you've probably done what I did. You bought a high-dollar, high-gain directional antenna expecting absolute crystal clear video for miles, only to slap it on your goggles, fly out 300 meters, and get hit with a wall of static. For literally years, I had this VAS Pepperbox Extreme sitting on a shelf collecting dust because I was convinced I bought a $75 dud. I tried it on box goggles, budget diversity adapters, you name it, and it choked every single time. Then I recently plugged it into a set of Skyzone 04X Pros, and suddenly I'm flying clear out past 1.5 kilometers like it's nothing. The antenna wasn't broke, I just didn't understand how antenna sweet spots and receiver limits actually work together. Today we're cutting through the noise so you don't throw away good gear or chase bad signals. First, let's talk about why high-gain antennas fail on cheap receivers. Think of a high-gain antenna like a patch or a phased array, like a giant funnel. Its only job is to scoop up massive amount of RF energy from one direction and shove it down the wire into your receiver. Now, if your receiver front end has limited dynamic range, which is common on budget diversity modules or cheaper box goggles, that massive flood of signal completely overloads it. It's like trying to pour a bucket of water through a tiny funnel all at once. It just spills everywhere. The receiver gets swamped or saturated, and instead of a clean picture, your screen turns into a staticky mess. High-end receivers like the Steady View modules in modern goggles have built-in filtering and hardware designed to handle high input power without clipping the signal. So if your big patch antenna acts terrible at short range, don't throw the antenna away yet. Your receiver might be the bottleneck. The second big piece of the puzzle is antenna tuning and sweet spots. When you buy an antenna, the box usually says something like 5.8 gigahertz, but 5.8 gigahertz isn't just one single point. It's a wide range of frequencies running all the way from around 5.3 gigahertz up to 6 gigahertz. An antenna might work across the whole range, but it is physically tuned to be most effective at one specific number. That's called its center frequency. At that center frequency, your VSWR, which is basically a measure of how efficiently the antenna translates RF power without reflecting it back, is at its absolute best. Look at this spec sheet, for example. Right near the top, it lists a bandwidth of 5.3 gigahertz to 6 gigahertz, but right above it, the center frequency is 5.65 gigahertz. That means 5.65 gigahertz is this antenna's absolute sweet spot. If you fly way up to Raceband 8, which is around 5.9 gigahertz, you're flying further away from where the antenna was built to perform. You'll lose range and get video breakdown much faster. Now, if we look at a standard FPV channel chart, Raceband 1 sits at 5658 megahertz or 5.658 gigahertz. That is within 8 megahertz of the antenna's tuned center, without needing a $500 vector network analyzer. Simply checking the spec sheet and setting your VTX to Raceband 1 locks you directly into the antenna's peak efficiency window. So, here are your 2 take-home rules for the bench. Don't judge an antenna on a weak receiver. If a high-gain antenna breaks up close to you, test it on a module with a better dynamic range before calling it a dud. Second, match your channel to your specific sheet. Stop picking random channels. Find your antenna's center frequency and set your VTX as close to that number as possible. We build our gear right the first time around here. No shortcuts. If this cleared up how signal chains actually work for you, hit subscribe, drop a question in the comments, and I'll catch you on the next build. Fly safe.